Okay, we're in 11.2 of Barnett, derivatives of exponential and logarithmic functions. So that's our goal for this section, is to be able to calculate derivatives of e to the x and ln of x, as well as computing derivatives of other log and exponential functions. And finally, we also want to be able to derive and use exponential and log models. So we'll do an example at the end. So how about the derivative of e to the x? Well, that proof is shown in the textbook, and we'll do it here as well. But one assumption that we need for the derivation of e to the x, the derivative of that, is this fact over here, that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. If you're having trouble believing this statement, or you're just not believing that that's true, plug in small values of h, values near 0 from both left and right, into this expression, and create a table, create a chart like we did in chapter 2, was it? And you'll see that the values are getting closer and closer to 1 as h is getting closer and closer to 0. So that's one way to verify the statement without formally proving it. We're going to assume it for free in the following process. And what's the following process going to be? Well, to find the derivative, we only know the 4-step process when it comes to e to the x. So let's do it. We're going to apply the 4-step process to e to the x. And the first step is to find f of x plus h. Well, if f of x is e to the x, f of x plus h is simply us replacing x with x plus h. Everywhere you will see x in the formula. So we get e to the x plus h, which is e to the x times e to the h. Remember, this is an exponential, right? So same base, different powers. When you're multiplying, you combine these two into a sum. So we're just going backwards of that rule here. Step 2 is to subtract f of x from that. So we have our f of x plus h. From it, let's subtract e to the x, right? This over here is the subtraction. E to the x is our f of x. So when we do that subtraction, we could factor out an e to the x. That's what's done here. It's a common term. And we're left with e to the h minus 1. So that's what we have in step 2. In step 3, we have to divide this difference by h, right? That's step 3, is divide by h. So we go ahead and we take our expression, e to the x times e to the h minus 1, and we divide it by h. And finally, in step 4, we simply take the limit as h approaches 0 of this quotient. So when we take the limit as h approaches 0, what we could do, I'm going to write it out here, the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. Well, what we actually get here is this expression. The reason being is this e to the x, well, x does not depend on h in any way. Remember, we're taking the limit as h approaches 0. So if we have e to the x, we could sort of treat it like a constant term and pull it outside the limit. So that's how we get rid of this e to the x and move it to the outside. Then it becomes e to the x times the limit as h approaches 0 of e to the h minus 1 over h, which is what's left. And what did we say at the beginning? We said we're going to assume for free that this limit is equal to 1. So we really get e to the x times 1 or e to the x. So the derivative of e to the x is e to the x. So f of x is e to the x, and its derivative, f prime of x, is also e to the x. Very interesting function, e to the x. It happens to be its own derivative. Now, be careful. There is in big red letters here, it says, caution, the derivative of e to the x is not x times e to the x minus 1. It is not. Do not make that mistake. That's a very common error for students to try and use the power rule when taking the derivative of an exponential function. But the power rule can be used here. The power rule applies only to exponential forms x to the n, where the exponent is a constant and the base is a variable. In fact, we call those power functions, if you remember, right? That's why it's called the power rule. In the exponential form, e to the x, the base is a constant, the number e in this case, and the exponent is a variable. That's how you can differentiate power and exponential functions, right? So you cannot use the power rule on exponential functions like e to the x. Be aware of that. Okay, so why don't we do some examples here? This one is 1/2 e to the x. Find the derivative of that. How do we find the derivative of 1/2 e to the x? Well, using the constant multiple rule, isn't that the same as 1/2 times the derivative of e to the x? And the derivative of e to the x we just found to be e to the x, so This is just 1 half e to the x. It's the same thing as what we started with. How about e to the x over 2? Now notice, the 2 moved to the power. The power is now 1 half x. Let me rewrite this here. This is e to the power of 1 half x. Think of it this way. How do we find the derivative of this one? Well, the secret to this is we need something called the chain rule that we're going to study in the next section. I'm going to leave the answer here, and I'm going to let you ponder why the answer is this. And perhaps you could get it. But again, we need something called the chain rule. So we'll come back to this example later on in chapter 11 when we do the chain rule. Okay, so just to think about it and to differentiate between these two, I wanted to throw it on here. How about f of x equals 2 e to the x plus x squared? Notice once again, exponential function, power function. Two different functions. The variable is in the power when you have an exponential function. It's the exponent, right? That's why we call it exponential. The variable is the base here. That's why it's called the power function. So the derivative of this one would be what? Well, the derivative of twice e to the x is twice the derivative of e to the x. The derivative of x squared is 2x. So really we have 2 e to the x plus 2x. We could factor out a 2 if we wanted to, and it would be e to the x plus x. Finally, the function here is negative 7x to the e power minus 2e to the x power plus e squared. Wow, this one is really trying to trick you. Let's break this down. The derivative term by term. The derivative of the first term is what? Well, we have a power function. Once again, x to the power of e. Remember, e is a number. So this is just raising x, the base, to some number power. So the derivative here is negative 7. Since this is a number, bring it down, e, and then this is x to the power of e minus 1, right? Because this is now a power function, we could use the power rule. That's the key. All right, how about the second term? Negative 2 e to the x. That's an exponential function. The derivative of e to the x is e to the x, so this is just negative 2 e to the x. Finally, for the last term here, e squared, e is just a number. When you square it, you get another number. The derivative of a number is 0. So this is really plus 0, which we don't normally write. And altogether, we get negative 7e times x to the e minus 1 power minus twice e to the x. So that's our answer. We could verify our answers here on this slide. And remember that e is a real number, so the power rule is used to find the derivative of x to the e, that tricky one here. The derivative of the exponential function e to the x, on the other hand, is just e to the x. Finally, the derivative of e squared, since it's a number, a constant, is 0.